Today we are going to discuss the entropy. The third law of thermodynamics states that entropy of a perfect crystal of an element in most stable form tends to zero as temperature approaches absolute zero. Entropy measures the randomness. What is entropy? Let us discuss. Entropy changes are fundamental to understanding the direction and feasibility of a thermodynamic process. Entropy is denoted by S. It is a measure of disorder or randomness in a system. The second law of thermodynamics states that for any spontaneous process, the total entropy of the universe remains constant. The property of the body which remains constant during adiabatic process is known as entropy. In order to understand this, let us consider let us consider three isothermals T1, T2, T3 and two adiabatic, say A and B. Since we know that in case of an isothermal process, temperature of the body remains constant, while in case of an adiabatic process, no external heat is supplied. When the gas expands adiabatically, no heat is extracted and when it is compressed adiabatically. So in first case, temperature of the gas is lowered, while in the second case it is raised. It is evident that neither the heat energy nor the temperature remains constant, and these two increase and decrease together. However, there is something in adiabatic process that remains constant just as the temperature remains constant in the isothermal process. The property which remains constant during the adiabatic process when no heat is supplied or extracted from the body is known as entropy. It measures the disorder of the system at the molecular level. Now, to get an expression, let us we are considering the three isothermals T1, T2, T3 drawn at a very small but equal temperature difference. Let NABA be two adiabatics which cuts this isothermal as shown in the figure in PV diagram. Now, if I consider Carnot cycle, say A, B, A, B, C, D. In going from A to B, some amount of heat Q1 is absorbed at temperature T1, and in going from D to C, amount of say Q2 is given at temperature T2. Thus, from Carnot cycle, Q1 minus Q2 by Q1 is equal to T1 minus T2 by T1, or 1 minus Q2 by Q1 is equal to 1 minus T2 by T1. Q2 by Q1 is equal to T2 by T1, or Q1 by T1 is equal to Q2 by T2. Similarly, if I consider cycle DC, say EF, an amount of Q2 is absorbed at temperature T2 and Q3 is given out at temperature T3. Therefore, Q2 by T2 is equal to Q3 by T3, which directly means Q1 by T1 is equal to Q2 by T2 is equal to Q3 by T3 is constant. Hence, if dQ is the heat exchange at temperature T in going from one adiabatic to another one, then change in entropy ds is equal to dQ by T. And total change in the reversible cycle ds is equal to 1 to 2 dQ by T. As T is constant in isothermal process, ds is equal to 1 by T, dQ is equal to Q by T. Unit of entropies are Joule by Kelvin. Now, some interesting points. Number one, entropy in a reversible cycle. Net change in entropy in any reversible cycle is zero. Let us take Example of Carnot cycle as an example. There is no change in entropy of the working substance during the two adiabatic paths. Either during adiabatic expansion or compression, Q is equal to 0. Therefore, delta S is equal to 0. However, there is an increase in entropy during the isothermal expansion as heat Q1 is added at temperature T1. Therefore, increase in entropy, say A, B, C, D. If I am talking about A to B, since Q1 is added to the system, delta S1 would increase. It would be given by Q1 by T1. There is a decrease in the entropy during the isothermal compression in which heat Q2 is rejected at temperature T2. Thus, C2D delta S2 would decrease, would be equal to minus Q2 by T2. Net change in entropy is delta S is equal to delta S1 plus delta S2 Q1 by T1 minus Q2 by T2. But Q1 by T1 is equal to Q2 by T2. Therefore, it is equal to 0 where net change in entropy is 0. A reversible process is an idealist concept where a system undergoes a transformation in such a way system and its surrounding can be restored to its original state by infinitesimal changes. Reversible process delta S is equal to dq by dt. T is absolute temperature, delta S universe is system plus surrounding is equal to 0. Carnot cycle सिंपल सा एग्जाम्पल देखे हमने जहाँ पर नेट चेंज इन एंट्रोपी कम्स आउट टू बी 0. Entropy increases in all irreversible process. Since all real process takes place in the universe are irreversible, there is continuous increase in the entropy. Entropy is not conserved. In this respect, entropy differs from energy. We can illustrate this by taking another simple example. Consider a small amount of heat dq radiated from a hot body A, hot, cold, at temperature T1, T2. Let dq be amount of heat is radiated from a hot body to a cold body at temperature T1 to a temperature T2. Therefore, for T1, since heat is going out, so entropy would decrease equal to dq by T1. For a cold body, entropy would increase by amount dq by T2. Delta S is dq by T2 minus dq by T1, and as T1 is greater than T2, therefore delta S is greater than 0. This indicates the direction in which process proceed in the nature. All natural processes are irreversible. They proceed in the direction of increasing entropy. Then we have Carnot cycle on the basis of entropy. Carnot cycle consists of following four processes. A reversible isothermal gas expansion process. In this process, ideal gas in the system absorbs Q in amount of heat from high temperature reservoir T, expands, does work on the surrounding, isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. Now, since amount of heat Q1 in isothermal AB A, B, C, D. एंट्रोपी चेंजेस फ्रॉम से S1 टू S2. ये हम ग्राफ ऐसे दिखाते हैं, TS डायग्राम. A, B, C, D. ठीक है. एंट्रोपी चेंजेस फ्रॉम S1 to S2. Since Q1 is absorbed, delta S would be Q1 by T1, or Q1 becomes delta S T1. From 2 to 3 or B to C, there is no change in entropy. Then from C to D, decrease in entropy, that is Q2 by T2, Q2 becomes delta S T2. Similarly, delta S4 would be equal to 0 from 4 to A. So energy available from work Q1 minus Q2, that is equal to T1 minus T2 delta S. Efficiency Q1 minus Q2 by Q1 becomes T1 minus T2 delta S upon T1 delta S. Delta S cancels out. Efficiency becomes T1 minus T2 by T1. This is Carnot cycle based on TS diagram. Some numericals, simple numericals based on entropy. Formula that we have to remember while solving the numericals for entropy is 1 S2 minus S1 is equal to Q by T. Further, change in entropy is given by, rather, S2 minus S1 is dQ by T, T1 by T2. Since dQ is equal to ms dt, therefore S2 minus S1 is equal to mc लिख लेते हैं स्पेसिफिक हीट के लिए, mc dt by t T1 to T2 is equal to mc log to the base e T2 by T1, where C is specific heat of water, specific heat, and specific heat of water is 1. Further, important thing, whenever a state is changed, then Q is equal to ml. L is latent heat. Latent heat of fusion is 80 calories and latent heat of steam is 540 calories. Now, for example, problem 1. Calculate the change in entropy when 10 gram of ice at 0 degree Celsius is converted into water. State change हो रहा है. So हम use करेंगे Q is equal to ml. S2 minus S1 is Q by T. Q is ml. 10 into 80, T is 273. Change in entropy ये आ गया. तो ये लिखा हुआ है यहाँ पर मैंने. Two ends of rod are kept at 127, 227. Calculate the change in entropy when 2000 calories of heat frost. Simply ये तो simple numerical है, तो ये तो हमारा change in entropy सीधा Q by T से solve हो जाएगा. ठीक है. Questions that are generally asked in the board exams: physical significance of entropy, define entropy, show that entropy in a reversible process is always positive, TS diagram, efficiency of Carnot engine based on entropy, TS diagram से. Define entropy, entropy for reversible and irreversible process. That is all in entropy. Thank you.